My plan for today, we're going to finish chapter 17. We're going to look at last year's test or so, and then and pretty much that'll be the plan for today. Well, I'm going to leave Friday for any questions, and then hopefully some sort of take-home test coming this Monday. Be one of those ones like we had last time where it's like you have a week or so, but I got to make sure I can get into contact with all the people who aren't currently like live streaming with me.
As you said, that'll be Monday.
They'll probably be Monday. I'm definitely not going to put it out anytime sooner than that.
Okay, sweet.
Now, I'll probably start the last couple chapters on Monday, but Wednesday we're going to have some. If it's the Wednesday, I think it is. Let's see. I'm not sure if it's next Wednesday or the 15th Wednesday. One of those Wednesdays, I'm not going to do a live stream. I'm going to just have it already pre-recorded and upload it because I got to go to Nashville for a doctor's appointment. So.
Do you have the coronas?
No, nothing that bad.
Are you sure?
Yes. Well, it's for someone else, and it's a doctor's appointment that was related to something else. But let's just say, yeah, I'm taking someone to Nashville. So, but it's not the coronas. Okay, so let's finish this chapter. Plan of test being posted on Monday, but I want to make sure I can get a hold of, say, some of our missing peoples before then. Okay, so let's just quick review of Ksp. So the idea of Ksp, just like our usual K expression, except that we don't have any essentially don't have any reactants. So our K expression becomes a lot easier to deal with. That is just products, and so K is equal to product times product. So our ice table is essentially just a big old zip with X's. So barium sulfate, we said Ksp is 1.08 times 10 to the 10th. So 1.08 times 10 to the negative 10th equals the products, barium, and sulfate. That's our K expression. Don't forget that. We don't include the reactants. We don't include the reactants because reactants are pure solids. Sulfate solid goes to Ba2 plus aqueous and SO4 2 minus. Our ice table, because this starts at 0 and 0. Because there's one of these, we have 1x. Because there's one of these, we have 1x. So our situation is just X and X. So barium sulfate, that's X and that's X. So we say Ksp is equal to X squared. So if I'm wondering how much barium dissolves or how much sulfate dissolves, it's this number equals X squared. So how do we solve for X? We take the square root of both sides. So when we take the square root of 1.08 and to the negative 10th, we got our 1.04 times 10 to the negative 5th. That's the concentration of barium. That's the concentration of sulfate. The concentration of both of those. Now, this is the hardest thing we'll see, lanthanum trifluoride. it's the hardest thing we could possibly see because it's what, like a triatomic. It's one lanthanum fluoride goes to 1 3 plus and 3 1 minuses. So just looking at this same situation, we have what? Select all. Let's just delete this. KSP. KSP is what? Like 2 times 10 to the negative 19th. 2 times 10 to the negative 19th. KSP expression is going to be what? Lanthanum 3 plus and fluoride 1 minus, but it's raised the exponent. So, and then when we write our ice table, we form 1 lanthanum and 3 fluorines. So 0, 0, X, and 3X. So we essentially have KSP equals X times 3X cubed, or 27X to the 4th. So that's the hardest thing we could possibly see. But how would you solve that? The same way. You would solve for X. You take this number, you divide by 27 because you have a 27 on both. Divide by 27 to get rid of this. Then you take the 4th root of your resulting answer, and that will give you X. Now, looking back at our ice table, this is X. So this is the concentration. If I'm asking the concentration of fluorine, it would be X times 3. That's the hardest thing I could throw at you for KSP. So it's okay. So right off the bat, I wanted to remind us of this before we jump into the last clicker question. For those who don't have clicker, don't have it pulled up, or too slow, remember, just send me an email. Send me an email with the clicker. Say, what is your answer? So identify the correct relationship between the solubility product constant and the molar solubility X for aluminum trihydroxide. So identify the correct relationship between KSP and X. There's another reason why I just showed you that. Hopefully to just remind you. Don't overthink this one. This is just like the lanthanum trifluoride example. So if I hadn't just shown you this, this would be a lot harder. Who the hell's talking?
Don't get rid of them.
Okay. So hopefully I'm getting some emails if you guys don't have clicker. Okay, so I'll give you another 15 seconds. I mean, I probably got most of them. Just want to double check if any last people. And okay. So correct answer. Oh. 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 It's E.
I got it right. Yeah.
So you gotta remember. So this is gonna form one of these guys and three of these guys, but the Ksp expression is products raised to the power of their coefficients. So 3 hydroxides means the 3x will not be to the first power, but to the third power. So x and 3x, so x times 3x cubed makes 27x cubed. X times x cubed would be x to the 4th.
Can you say that again? The raised to their coefficients, you said?
Yeah, raised to the power of the coefficients. This is our basic KSP thing. If
Right.
I have, always late, but okay. So remember, every K expression is going to be, I have A plus B goes to 2C. The K expression, well, would have been C squared over A times B. Well, in the case of A and B are solid, well, then those guys cancel out and we just have C squared. So with our aluminum trihydroxide, we're going to break apart into 1 aluminum and 3 hydroxide. So you're going to have aluminum times OH cubed. So don't forget, this is all based on our KSP. It's all based on our K expressions. So this is all based on our K expressions. So can't forget that. Now there's a few more things we're going to talk about for this chapter, but these aren't really too testable. But they may be on some of the homework. So common ion effect. Common ion effect is essentially Le Chatelier's, but for solubility. So it has the same effect as we do when we deal with weak acids. If we have a lot of a common ion in a solution, this will drastically decrease the amount of solubility for the other guy. So for example, silver chloride has a certain solubility if it's neutral solution. But if I, for example, add a bunch of sodium chloride, which has a secondary source of chlorine, we are going to get less silver dissolving. Now, the same thing can be said about basic insoluble salts, like magnesium hydroxide. Under basic solutions, magnesium hydroxide is poorly soluble. Under neutral conditions, it's more soluble. Under acidic conditions, it would be the most soluble because the hydroxide, when it dissolves, will neutralize the acid and thus go away. Le Chatelier says you remove the product, you shift and reform more products. So under acidic conditions, we see a greater solubility for magnesium hydroxide. Under basic conditions, you see less solubility for magnesium hydroxide. Essentially, we're having the Le Chatelier's except for solubility. Now, please note, dissolving more magnesium hydroxide, putting more magnesium hydroxide into the liquid does not mean more will dissolve, because remember, the solid plays no part in the K expression. And then this is the last thing to talk about. We're not really going to do this on the homework, but you can have a K for complex ion formation, these Lewis acid bases. Nickel hexa aqua, example of colored complex. Iron thiocyanate, we saw that in lab. Silver cyanide is another one. we can have these guys forming in solution where the anion, we wouldn't predict this sticking on there, but when it sticks, it forms a complex ion that's going to actually be separate from silver plus. So this can be neutral species or it could be a charged ion, but they all result in a special complex that is rather than a solid salt. So what makes a complex different is a complex is still charged. If I formed a salt, like iron thiocyanide, where there's 3 thiocyanide, you would have a neutral solution. But this guy, you notice, is still charged with 2 plus. So this is a complex that forms that's just 1 iron with 1 thiocyanate, not like you would expect with 1 to 3. So now these guys will have a K expression for the formation, and it can just be treated like any other K expression. This is what we did in lab. We said, oh, 1 iron, 1 thiocyanate go to form an iron thiocyanate. And we tried to find the K expression for this. We treat it just like any other K. But the only reason I bring this up is because these complex formations can lead to surprisingly increased solubility of insoluble salts. So, for example, silver cyanide would take silver plus out of solution. So if I add cyanide to silver chloride, the solubility of silver chloride would increase because the silver that dissolves is being used up to form this weird complex here. So we can get an increased solubility by mixing in something else in. But as I said, that is all I have for this chapter. That's chapter 17. So the big test is going to be over chapter 16, chapter 17. We're going to talk about what it means to be an acid and a base, what it means to be a Lewis acid, the various definitions, how to calculate pH of a weak acid, how to calculate pH of a strong acid, how to calculate H plus from a pH. We're going to talk about buffers. We're going to talk about some titrations, but not too many. So this, so you should be able to see this. This was the exam I gave, well, 2 years ago. This was, so please note, on this case, I did not give you the Ka value, but since this was a take-home there, you were expected to look up whatever Ka value and state, this is a Ka I got from whatever source. So you could find this on Achieve, you can find this wherever, and you could use that. So I'm going to quickly look through the problems and then we'll work through these guys. So what is the pH of the following 4 solutions? Perchloric acid, nitric acid, boric acid, and ammonia.
Is that the one we're going to use an ice table for those, right?
Nope. Well, technically you have to use an ice table for the weak acids or weak bases, but not really because there's the repetition of the same type of acid. Then what acid and conjugate base pair would achieve a buffer with pH 2.7? Justify your answer. What concentrations of H plus in the following solutions? Answer the following K-related questions for this, and then it's a consecutive thing. I think I did this over K 15, 16, and 17 that year. So let's say based on so we have write the K expression for that guy. If Kc with concentration this, and this, what is Kc? Turn Kc to Kp. So that's chapter 15 stuff. Based on your Kc value, if the concentration is this, and this, what direction will it shift? Sorry. Oh, what the? Okay. Kc would, and then based on the Ksp of this. Okay, that's a separate one. Based on the Ksp of this, what would the pOH of 50 grams of this be in water? So if I give you, this is how much is dissolved, like find how much hydroxide would you have? Answer question on this graph, titration of 60 mils of a weak acid with an AOH. So what is the concentration? Then what is the Ka? What is the pH of the following buffers? You may need the pKa or pKb, so you'll have to look those up. Solution of this. Solution of this. Answer the following questions regards to this iron thiocyanate complex. So this is kind of based on the lab. Considering it's like, if I have this, what is the Kc when? So this is just like the lab. Initial equilibrium. So we find out what are those guys at equilibrium and then find our K. Considering this reaction, what happened to the concentration if you added HCl? So you got to think about Le Chatelier's and common ion. This guy, what is the equilibrium concentration of silver ammonia? It would be present when you have this concentration, Kc. Then classify these as Lewis, Bronson, Lowry, or Arrhenius, and mark them as acid or base. So you just classify. So this was the take-home test. So we'll just work through this bit by bit. I'll have to consult my big old book of numbers for KAs rather than try to Google this. But please note, you could easily Google this. If you have a book, you could look this up in the back, but since we have Achieve, we could easily go to there and find the link. So, okay, let's start with the easy ones. I'm gonna minimize this down so we at least see them both on screen. So, perchloric is a strong acid. How would you know that? Two ways. You look at the list of strong acids, or you try to look for a K and you don't find one. You look for perchloric and it just says strong acid or big or doesn't give you one, or it's a number that's much bigger than 1. So you say, oh, for a strong acid, pH is just negative log of the concentration of your acid. So I just say, well, negative log of 6.7 times 10 to the negative third. And as this is a take-home, as this is a take-home test, you would need to show work. You can't just go blah, 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 magic. Here's the answer. You would want to show the work of this is what I did to do this. So I'll go ahead and answer these questions, and then I'll have to close this out because we're running out of time and start up the next one. So negative log of that. Negative log of this number gives you
2.17.
Yep, 2.17. That's correct. Now, nitric acid, B, also a strong acid. Same thing. You look up for the Ka, you do not find one. So it's just negative log of this. That's all you have to do.
So if you look it up and you can't find one, then it's a strong acid?
Yes. If you look up this term, aqueous equilibrium constants or acid dissociation constants, and you cannot find one, or you cannot find one that, if you cannot find one that is smaller than 1, then it is a strong acid. These guys would have Ks in water like 100, 1,000. Ks that are bigger than 1. Ks that are bigger than 1. Because of that, we have it's a strong acid. So this guy is 1.3. 1.3. I'm going to finish these 2 problems and then I'm going to stop and restart this. I want to finish all of question 1. Now, boric acid. You look up boric acid, and you get that boric acid has a Ka of 5.8 times 10 to the 10th. So Ka is 5.8 times 10 to the negative 10th. So, it's weak. Now, yes, you might have to use the ice table, but no, do you really have to use the ice table? You can say that the pH, well, you can say that Ka is equal to x squared over the concentration of your acid. Almost all of the ice tables simplify to that. And then your concentration of acid is equal to the square root of HA times your Ka. So square root of 3.5 times 5.8 to the negative 10th is 4.5 to the negative 5th. 4.5 times 10 to the negative 5th. I ran out of room. Oh, too far. 4.5 times 10 to the negative 5th. So that is our H plus. The negative log of that will give us our pH. So negative log of 4.5 times 10 to the negative 5th is 4.34. So the pH of this one is 4.34. So what did I say? 7. Zero. This one. 4.3. The last one, it is a weak base. You look this up, and you're probably going to find not the Ka, but the Kb. You're going to find the Kb of this guy. Kb of ammonia is equal to 1.8 times 10 to the negative 5th. Now, you still get the same expression. Kb equals x squared over the base, and where x is our OH. So OH minus is equal to the square root of our base times our Kb. So we get this repetition. So 1.045, the square root of 0.0045 times 1.8 times 10 to the negative 5th gives us 2.8 times 10 to the negative 4th. Now this one might actually be a one that you need quadratic for, but I'm going to fudge it, and we're not going to do the quadratic right now. Now, as we do the negative log of this, note, this does not give us pH, because this is OH minus, this gives us POH. So the negative log of this gives us 3.55. So 14 minus 3.55 gives us the pH of 10.45. 10.45. So this was, oh shoot. So that was all of question 1. I'm going to go ahead and stop this, and I'll start the next one in just a second. I'll share.
I got a quick question.
Yes?
How did you know for, I think it was C, Well, how did you know that you couldn't just do the negative log? How did you know that you had to do all the extra stuff?
First, okay. When I look up the Ka, I find out there is an actual Ka expression. When I look up the dissociation constant, I find this is a weak acid. So step 1, we check, is it a weak acid? Step 2, if it's not a weak acid, we can skip to the end. If it is a weak acid, we have to do the extra steps.
Okay, makes sense.
We always check and see, is it a weak acid or is it a weak base? Okay,
So if it's a weak base or a weak acid, then you have to do the extra stuff.
yes. Okay, as I said, I can re-answer this in like a minute or two when I reopen this. So I'm going to stop this meeting and see you in a minute. As I said, test most likely going to be started on next Monday. You have like probably a full week, but I really need to get a hold of the few people who are,
KIA.
who aren't necessarily, I don't see every day.
MIA, KIA.
Well, I mean, some people just are literally working like every day, and so working in the morning, and so they can't really be expected to find time to like live stream, and I can't really hold it against them. So okay, so a quick reminder. So as we look at these, the step 1 is determine whether it's a strong acid / base or weak acid / base, and we do that by looking to see whether you find a Ka or Kb associated with it. Now, if in my book right here, I'm not sure. Oh wait, I'm not sure how well you can see this, but you see if you look down there for under sulfuric acid, you'll see it has a Ka that just says strong. And the second Ka2 is 1.2 times 10 to the negative second. Anytime they have a Ka that is strong, it's either going to be much greater than 1 or just going to say strong and just leave it at that. So you want to look and see whether it's a strong acid or a weak acid, and then that's going to determine how we treat it. For a strong acid, strong base, it's basically we can do this.
Negative
Oh,
log.
this is the step. You say HA equals H plus. That's step 2 for a strong acid. For a weak acid, we have to say H plus equals the square root of HA times Ka. So both of them have a step 2. This is for a strong acid. This is for a weak acid. It just literally, for a strong acid, you say 1 equals 1. You don't actually have to do any math. And then both of them for step 3, it's just negative log of H plus. The only problem is then if you have a base, you have to turn the negative log of OH minus into H plus, into pH. So, okay. Okay, get back to this. So we did all of 1. 2, what acid conjugate base pair would you use to achieve a pH of 2.7? Now, what you got to remember is the hard and fast rules of buffers. And that's that for a buffer, it's usually good for up to plus or minus 1 pH unit from the pKa. So what you want to do is look at a list of Kas and find the pKa. find which pKa is within plus or minus 1 pH unit of 2.7. So that when you're just looking at a list of Kas. So remember, how do you find the pKa? So don't overthink this one. This one is the easiest 5 points. It's pKa is just the negative log of your Ka. Now, another hard and fast rule is, so for example, 1 times 10 to the negative third, if I take the negative log of that, that's going to give us 3. If I have, for example, anything greater than 1 to the negative third, so say 2 times 10 to the negative third, the negative log of that's going to be, it's going to be less than 3, is going to be what? Less than 3. So we want something in the range of, so 1 times 10 to the negative fourth is going to be equal to 4. We want, if you can look here, hard and fast, looking at this, for 2.7, we want something that's going to be in the range of, we don't want anything that's in the range of 10 to the negative fourth. We want something in the range of 10 to the negative third or 10 to the negative second. So you just look at a buffer and try to find one that is in that range. So I'm looking down my list. I see arsenic acid, which has a pKa of 5.6 times 10 to the negative third. So I take the negative log of that, and I say, what is the pKa? The pKa of that is 2.25. So 2.25 for arsenic. Would that work? Is that within plus or minus 1 pH unit of 2.7?
Yes.
Yeah. So that is a possibility. That is a possibility. So you would say I would mix in this. I'd mix in ASO4 and H2ASO4 1 minus. I'd mix in that because the pKa is 2.25.
Huh?
So now that is one possibility.
Hitting bricks.
That is one possibility. I keep looking down my list. What about chloroacetic acid? Chloroacetic acid is pKa of 1.4 times 10 to the negative third. I get that is a pKa of 2.85. Well, that's even better. 2.85. So chloroacetic acid is it's ugly, but we can do HC2 H2O2Cl 2O2Cl, and then you'd have C2H2O2Cl minus 1. So I removed my H from in front, so that's my 2 compounds I would use. And that would give me a plus or minus within 1 pH unit of 2.7. And I could keep going. I could keep going and find various different ones that would work. I could use malonic acid, which would give us a pKa of 2.82. So there's many, many, many different options. The only rule is that you have to have a pKa between 1.7 and 3.7. If it's any farther away, it's not going to be very good. So that's all you'd have to do for that one. You would just say, oh, I could say 2.82, and then I'd have a mixture for HC2 H2O2Cl slash C2. I'm not gonna bother to subscript any of this. I'm just being lazy. 2Cl. But we could easily do that. There's my answer. And your justification is just like this has a pK of 2.82, which is 2.85, which is within plus or minus 1 pH unit of 2.7. Now, what is the H plus concentrations of these guys? This one, not meant to be like overly strenuous. We're just going from pH to pKa, or from strong, or from basic to acidic. So these are some equations that we expect you to know. If pH equals negative log of H plus, then H plus equals 10 to the power of negative pH. So 10 to the power of. Now here's the weird thing. This would work even in a weak acid. Even in a weak acid. Because the H plus is still dependent on the pH. So this is a strong acid, but we could easily say this is a weak acid and we'd still get the same result. So we do this, you get what? 1.99, so let's say 2.0. 2.00 times 10 to the negative fourth. Easy peasy. Now this guy, this is a base. This is a molarity of base. Remember, Kw equals H plus times OH minus. So I can say Kw divided by OH minus equals H. So I can say, well, at 1.7 times 10 to the negative 6, so 10 to the negative 14 divided by 1.7 e negative 6. Now make sure you're either using parentheses or using the capital E notation, or else you're going to get a number that's way off in a different direction. You should get 5.88 times 10 to the negative 9. But sometimes you can multiply by 10 to the negative 6 when you mean to divide by 10 to the negative 6. And instead of 5.88 times 10 to the negative 9th, you get 5.88 times 10 to the negative 21st.
How do you know that that's your okay, all right, all right.
When you multiply those two back together, you should get 10 to the negative 14th.
Is it 14? Was it 14?
Yeah, 10
It's
to the
14.
negative 14th. That's our KW.
Okay, 10 to the negative 14.
Mm-hmm. Now, since we already covered chapter 15, I'm going to go ahead and skip 4. But so based on this, okay, skip straight to 5, a KSP problem. Now, once again, I do not give you this KSP, but you can look all these up. You would just say Google solubility product. You could Wikipedia solubility product of this. Now, I know, all your professors tell you, don't use Wikipedia, it's not reliable. It's usually pretty reliable for most scientific data. Because who the hell is going to hack that, to change that, to like screw up a bunch of people? Not like we're arguing about the legacy of some politician, where it's like, one side's going to change it to say one thing, the other side's going to change it to say the other. No, there's not any magnesium hydroxide deniers out there. At least I hope not. I would be very, very sad.
The dark side.
Teach the controversy. So there's our KSP. So hypothetically, first, let's check out what is the maximum solubility of this. What is the maximum solubility? Well, the KSP expression is going to be Mg OH squared. Okay? OH squared. And so our ice table is going to simplify down to 0, 0, x, 2x, so that this is x and this is 2x. 2x squared is 4x squared. 4x squared times x is going to be 4x cubed. So with that in mind, solving for x, 1.6 times 10 to the negative 12 divided by 4 is 4 times 10 to the negative 13th. Now, the cube root of that gives us x. So x is equal to, x is, x is equal to 7.3 times 10 to the negative 5th. Negative 5.
What'd you get for it?
7.3 times 10 to the negative 5. 7.37 if you want to
7.
if you want to be very accurate. But okay,
So that's for the Mg, but then you're going to have to do.
you would have to double that for the hydroxide. Now, hypothetically, is the 50 grams greater or less than, going to give you greater or less than that concentration? So 50 grams divided by my molar mass, well, magnesium is 24 and oxygen is 16. There's 2 oxygens, so 32, plus another 2 from the both hydrogens would give us 0.86 moles divided by our volume of 100 milliliters. So this hypothetically should give us 8.6 molarity. But obviously that's not going to be the case. So yes.
So you would square the 7.37, right, to get your OH.
You 7. No, you would just double it.
Just double it. Times it by 2. Okay.
Times
okay.
by 2. So this concentration, 50 grams, is way too much. Not all of this is going to dissolve. I should have checked that from the get-go, but not all of that's going to dissolve. So this X is valid. Now to get OH, we're going to have to times that by 2. So 7.37 times 2 means the OH concentration is equal to 1.47 times 10 to the negative 4th.
Wait, your times in that number by 2?
The 7.3, yes.
Yes. Okay. Get the OH. Right. Okay.
Okay. Now, finally, the question specifically asks, what is the POH? So if I take that number, if I take the negative log of that number, mute your mic,
Well,
you fool.
I didn't close the concrete, puto. Hey, pendejo! I didn't close the garage door. Yeah, I didn't close the concrete. So don't be yelling at me, puto.
Yeah. There we go. Okay. Sorry. Some people. So with that in mind, we take the negative log of this number, which is our concentration of OH, and that gives us our POH. So the answer for this question, what is the POH of magnesium hydroxide solution? You would get a POH of 3.83. 3.83 POH. This is, as I said, this is a little bit of a difficult problem. Maybe this should have been worth a little bit more than 5 points, but keep in mind, you show work along the way, you get points along the way. Now 6, this should be one of the easiest problems if you know how to treat this. You know how to treat this. If you know how to treat this. Okay. This is a titration problem, just like some of the labs. We have 60 mils of weak acid. We have 0.1 molar base. So we have to figure out what is the concentration of the weak acid. Now this number is regardless of whether it's weak acid or strong acid. We literally are going to say MAVA equals MBVB. So all we have to do is say, what is the volume that we see the big jump at? 30 mils. What is the concentration of the base? 0.1 molar. What is the volume of the acid? 60 mils. So it just becomes, as I said, MA, which is what we're solving for, VA, 60, equals MB times VB. So 0.1 times 30 divided by 60 would give us our concentration of acid as 0.05. 0.05. Easy as we can make it. Now, as I said, this could be strong acid, strong base, weak acid, weak base. Doesn't matter. It's got to be the same. Now, this next part is weak acid or weak base specific. You cannot do this for a strong acid. If you do this for a strong acid, you will get it wrong. You cannot do this for a strong acid. So, the Ka of a weak acid can be determined by looking at the half equivalence point. So this is our equivalence point, 30. The half volume would be 15. So from there, 30 to 15, what is the pH at that? The pH equals pKa at that point. So this one you would have to approximate. Half of that is 3. So it's a little bit above 3. 3.1, 3.2. I conveniently have this labeled 3.2. But 3.1 would be fine. It's a little bit above 3. 3.3 would also be fine. pH equals pKa at half equivalence point. At half equiv. So I ask you for what is the Ka. So 10 to the negative pKa is going to give you your Ka. So you would say 10 to the negative 3.2. Or you get 6.3 times 10 to the negative fourth. 6.3 times 10 to the negative fourth. Now, this number would vary for you depending on what you declared your pH to be at that point. So it gets a little bit trickier depending on how you use it. So this would be a range of values, but that is acceptable. That is acceptable. So that's something we have to keep in mind. So that's probably where we're going to stop for now. Stop that for now because we're out of time. We will continue this on Friday. Bring your questions, bring your whatever. If you have any if you have any questions on the homework, I'll try to help you work through them. But in the meantime, just keep working on the homework. Keep sending me any specific questions you have, and we'll finish this test up on Friday.
Hey, Dr. Evans,
Yes.
do you have time after your 1 o'clock class or after your class going on around 1 o'clock?
Yeah.
Okay. Can I just have a couple questions like for the lab and stuff?
Yep. That's fine. That's fine.
Okay,
Just-
awesome. Thank you.
Yep. So we'll go ahead and end this for